Hey everybody, my name is Nick Bright, and this is my video for my final galvanized capstone. So if we give you a second. All right, great. So my project was about forecasting energy consumption by predicting national and regional energy usage based on historical trends. The motivation behind this project is that as we transition towards renewable energy, we're going to need to know more about how to accurately forecast our demand so that we can do things like store solar energy and wind energy because they're a little bit more difficult to manage than traditional fossil fuel electricity generation. So a little bit of background about how our electrical grid is structured. There are 68 balancing authorities nationwide. Each one of those little dots you see on the map there is a balancing authority, and they are broken up into 13 different geographic regions. For instance, there's California, Arizona, Florida, but then also the Midwest, the Northwest, New England, things like that. Each of these balancing authorities does a hourly energy forecast 24 hours in advance. So they're predicting tomorrow's energy usage today. And the objective is to minimize the difference between energy demand and the energy generated. Basically, you want to have how much energy you're generating be as close to how much energy is needed as possible, so you don't have brownouts or blackouts or anything like that. And also so you're not putting undue burden on our electrical infrastructure. Unfortunately, because of the number and sort of geographical distribution of these balancing authorities, there is a little bit of mixed reporting, which I'll get into in the next slide. So the data itself, as I mentioned, it's nationwide hourly demand generation data going back to mid-2015. Of those 68 balancing authorities, 10 of them do not report demand or forecast, only generation. And there's 2 balancing authorities that don't even report net generation, mostly because they're not large enough to warrant regular updates or reporting or anything like that. And the EIA, which is the Energy Information Agency, posts this data from balancing authorities as is, which means whatever kind of issues are in the data as they get it, they don't go through and fix it. So just a quick little summary of the work that I do to clean the data: remove some unnecessary columns, change the index, added some generation source columns for some of the older data tables. They basically didn't track how much energy was being generated from things like wind, solar, hydro, stuff like that prior to mid-2018. So I had to fix that and then fill in some missing values from some of the bad data. So the first model I decided to work with was an ARIMA model, which stands for Autoregressive Integrated Moving Average. And that works really well for time series data because instead of taking a set period of time to train your data on, it's on a constantly moving window. So instead of trying to predict October with January's data, you're trying to predict the first week of October with the last week of September. I broke my data into a 2/3 test train split, which means the first 2/3 of the data were for training the model, and the last third was for testing the model and seeing how it performed. For my baseline, I didn't do anything about the bad values in the demand column, and I shifted the baseline to train from previous values. So as I mentioned with that moving average window, it's training on yesterday's data to forecast tomorrow. So the measure of success for this kind of a model is the RMSE, the root mean squared error. That's typically something you want to be as low as possible because it measures the variance between what you predict and how the model actually performs. So with my baseline, I got an RMSE of 66, almost 67, which wasn't great. So I took a couple of approaches to try and fix that. The first of which was to plug in zeros for the missing values in the demand column. But that actually made my model perform a little bit worse, which makes sense if you think about it, because the balancing authorities that don't report, they have lower demand and lower generation, but it's still not zero. So as you can see here, the RMSE was up to 220 from 67. I then tried to replace those null values with the mean of the baseline reporting that I did have. So I just took the average, which as you can see here is 343, and plugged that in, but that made the model perform even worse, which again makes sense if you think about it, because the places that aren't reporting are likely going to be below the mean in terms of their demand. Unfortunately, that was about as far as I got. I had some technical issues, and so I had to start over a couple of times. But that brings me to my final slide, which is future work and next steps. So one thing I'd like to do is see if any of the columns I discarded in the initial stages were actually valuable and might have good insights. I'd also like to model individual regions. So instead of doing the nation as a whole, break it down into different areas. There is a trade-off where the model might perform better, but it will be less transferable to other regions that are different. I'd also like to incorporate some external factors such as climate, weather, population, things like that, because presumably when it's really hot, really cold, energy use goes up as people are using the AC and the heat, and the more people live in a certain area, the more net energy is going to be demanded. And then I also like to look for trends in the sources of energy generation. As I mentioned, some of those columns have wind, solar, hydro. I'd like to see how those are distributed geographically and over time, and if there's any trends. And then most importantly, back at my work, so that when my computer crashes, I don't lose everything. So thank you very much. That was my video.